organic compound containing a hydroxyl group attached to an alkyl group. Hydroxyl group is OH. That is hydroxyl group. An alkyl group is any hydrocarbon. So CH3, CH2, whatever. Okay, this is your alkyl group, which is a hydrocarbon. This is a hydroxyl group. That makes up an alcohol. So alcohols have the general formula ROH, where R is your alkyl group and attached with a hydroxy group. Okay, so the characteristic function of these alcohols and phenols is the hydroxyl group. Okay, remember we talked about phenols a little bit also? Phenols are a benzene ring, which is a 6-member ring with conjugated double bond system. Been very stable and has an OH group. Okay, that is a phenol. Okay, so phenols also have a hydroxyl group and they're considered alcohols. Okay, alcohol is a general structure ROH, in which R is any alkyl group. Phenols are similar in structure by containing an aryl group in place of the alkyl group, which means it's a conjugated bonding system. It's an aromatic compound. So instead of an alkyl group, it's an aryl group. Both can be viewed as substituted water molecules in which one of the hydrogen atoms have been replaced by an alkyl or an aryl group. Okay, so remember the formula for water is H2O. Why did you go back? Okay, formula for water is H2O. So hydrogen, oxygen, hydrogen. So one of these hydrogens is replaced by an alkyl group or an aryl group. That's an alcohol. So it's a replacement of water molecule. It has similar properties like hydrogen bonding, things like that. Okay, so here's this is your functional functional group for alcohols, ROH. This is a similar group. This is a phenol. Again, R is just replaced by a benzene ring. And our R group here is CH3. So CH3 is one carbon. What's the name for one carbon we talked about? Was methanol, right? So there was methane. So this is methanol with the alkyl ending. Okay, because there's only a one carbon group on it. We're going to name it in just a second. So here's your alcohol. There's your phenol. And this is methanol. The OL ending is what determines the alcohol. The CH4 is methane. You drop the E and add OL because it's one carbon. So it's methane. So you drop the E and add OL. Once you see OL, you know there's an OH group because it's an alcohol. Ethers. Ethers have two alkyl groups. So both the hydrogens in the water molecule are substituted now. So you have two alkyl or aryl groups attached to the oxygen atom and be thought of as substituted alcohols. Okay. So the functional group is R, O, and R prime. The prime goes right there. They don't have to be the same. It could be like, let's put CH3, O, CH2, CH2, CH3. That's an ether. There's two R groups attached to the oxygen. Both hydrogens of water have been substituted now with alkyl groups. Okay. It can be a phenol group or it can be a regular alkyl group. Well, let's get some of that out of the way so I can see the group. Okay, thiols. Thiols are like alcohols. Okay. The only difference between a thiol and an alcohol is instead of OH, you have SH. Okay, if you look at the periodic table, S is directly below oxygen. Has the same 6 non-bonding electron pairs, same Lewis structure, so it behaves chemically the same way. So SH and OH are going to be similar in their reactions. Okay, so instead of alcohol, they're called thiols. Okay, and they contain the sulfur hydryl group SH instead of OH. Okay, so ROR is an ether. Okay, 2 R groups that's a functional group. And this could be methyl on both sides. You have dimethyl ether or methoxymethane. How we name, we'll get to naming a little bit in this chapter. Okay, RSH is your thiol group. Okay, And if you have a methyl group attached to it, it can be methane thiol. You just add thiol at the end. Remember, methane is CH4. Substitute one of the H's with SH, and not because of thiol group. Then you write the name of the alkyl group, methane, and add thiol to the end of it, which means there's an SH group attached to it. Okay. A lot of your biological molecules, like sugars, carbohydrates, fats, lipids, and proteins, contain hydroxyl and or thiol groups. Look at glucose, which is a sugar we use for the brain. We'll do a lot of glucose later on. Okay, we have OH groups attached. Okay. We have galactose. We have OH groups attached. These are alcohols. They're carbohydrates. And fructose. We have OH groups attached. Okay. And we'll learn how to name those, what the different important structures are in those later on in chapter 15 or 16. Okay, dithiol. Okay, dithiol theoretical. This is 2 thiol groups and 2 OH groups. So here's your dithiol. And here's your di-OLNE for alcohols. Okay, so you've got 1, 2, 3, 4 carbons. You got 2 OH groups and 2 SH groups. That's dithiol-3-etol. Okay, so in lots of biological systems, the hydroxyl group is often involved in a lot of reactions like oxidation, reduction, hydration, and dehydration. We did a couple of those already with the alkenes with the double bonds. We did hydration reactions, and we did dehydration reactions yet. But we did hydration reactions. We added OH and H across the double bond. Okay. Oxidation is the gaining of oxygen. Reduction is the loss of oxygen. Hydration is adding water. Dehydration is taking water away. Okay. In glycolysis, which is the metabolic pathway where glucose is degraded and energy is harvested in the form of ATP. We'll go in all those steps through all the glycolysis later on in the chapters. Several steps center on the reactivity of the hydroxyl group. That's where your reaction gets its start at. The majority of consumable alcohol in the world is ethanol. Okay, ethanol is your vodka, your rum, your scotch, your brandy. That's all ethanol. Ethanol is 2 carbons, okay, and an OH group on it. So ethanol is CH3, CH2, OH. That's ethanol. Okay, that's what makes all our alcohol. Produced by fermentation reaction carried out by yeast. Okay. The thiol group is found in the structures of amino acids. Okay, as we do the amino acid building blocks of proteins. That keeps your proteins in the proper 3-dimensional shape that's required for their biological function. If your proteins become denatured and lose their shape, they will cease to function. Okay, the body recognizes things by shape, like a lock and key mechanism for things to be stimulated and for reactions to occur. Okay. So the functional groups of OH and SH, the thiol groups and the alcohols, play a central role in the structure and chemical properties of biological molecules. Okay, so we're doing a lot of studying with the OH and SH groups. Polyols. Polyols are, poly means many, OLs mean alcohol or OH. So many OH groups. Okay, that's what is sugar. That's what glucose is. There's multiple OH groups on it. Okay. So research has shown that even as babies, we demonstrate preference for sweet taste over all others. People like things that taste sweet. That's what keeps me in business. It causes tooth decay, causes all kinds of fun stuff. Okay. There are many reasons to reduce our intake of refined sugars, in particular sucrose or table sugar. Okay. You want to reduce your intake of refined sugars. Okay. Too many people eat high calorie, low nutritional snacks rather than more nutritious foods, which can lead to obesity, causes type 2 diabetes, causes heart problems, and kidney failure, a lot of other problems with the body. Okay. Sucrose. That is what's responsible for tooth decay. Okay, that's a refined sugar. Lactic acid is one of the products of metabolism of sucrose. When you break down sucrose by bacteria in your mouth, it produces lactic acid. Lactic acid dissolves your teeth enamel. That results in a hole in the tooth. That results in a cavity. Okay. So when sucrose gets dissolved, metabolized by bacteria, it produces lactic acid. And this acid is what dissolves teeth, dissolves the tooth enamel. So you have to have two things in the mouth for decay to occur. You have to have the bacteria, and you have to have a form of food source, like sucrose. Okay. For those with diabetes, glucose intolerance, or hypoglycemia, sucrose in the diet makes it difficult to maintain a constant blood sugar level, cause it to fluctuate. You go in the nursing program, you realize how much sucrose causes trouble. If you take sucrose out of the diet, you removed a lot of food source for a lot of bad things that go on in the body. Okay, one of the big things we do with cancer treatments, okay, is remove sucrose from the patient's diet. Because the cells lack their food source, they don't grow as rapidly. Food chemistry industry has invested billions of dollars in the synthesis of sugar substitutes. Okay, sweet and low and all those other ones. Okay. We recognize such as aspartame, which is equal or NutraSweet, saccharin, which is sweet and low, or Splenda. They're common non-nutritive sweeteners worldwide. This is particularly place of sucrose, but they have their problems of their own too. We also buy products including candy, soft drinks, gums, which are advertised to be sugar-free. But most of these are not free of calories. They're free of sugar. They just have sugar substitutes, which still have calories in them. Okay. A check of nutrition labels reveal that these products contain sorbitol, mannitol, or one of the member classes called sugar alcohols or polyols. Multiple OH groups taste sweet. Okay. And they do have calories to them. Sugar alcohols are found in many foods like fruits, vegetables, and mushrooms. Okay. Others are made by hydrogenation or fermentation of carbohydrates from wheat or corn. Remember what hydrogenation is? Hydrogenation means the adding of hydrogen across a double bond. Okay. That takes it from a unsaturated to a saturated hydrocarbon, which increases its stickiness and makes it more of a solid. Okay, all are natural products. Okay, compared to sucrose, they range in sweetness from about half to nearly the same. They also have fewer calories per gram than sucrose, about 1/3 to 1/2 the calories. Okay. Polyols are also a cooling sensation in the mouth. Okay. You know how alcohol evaporates very quickly because of the OH group? That's what the polyols do too. The alcohol also gives you a cool sensation because of evaporation. Okay. The cooling is caused by negative heat of solution. They absorb heat from the surroundings so they can dissolve in order to advantage in breath fresh mints and gums. Okay. Breath freshening mints have that ability to absorb heat from the surroundings, so it acts as a cooling effect. It gives you that cooling taste. Okay. Sorbitol is the most commonly used sugar alcohol. It's about a little more than 1/2 times the sweetness of sucrose. Sucrose contains 4 calories per gram. Sorbitol is about 2.6 calories per gram. Now you'll notice a capital C when we talk about calories. Remember, a calorie is the amount of energy it takes to raise 1 gram of water 1 degree centigrade. A capital C is a kilocalorie, 1,000 calories. So when your Snicker bar says it's 7.3 calories with a capital C, that's 7,300 calories. Units of water. Okay. A capital C means kilocalories by 1,000. Okay. So when you see the capital C in the stores, realize what you're looking at. Discovered in 1872 in the berries of Mount Ash trees, sorbitol has a smooth mouthfeel, which makes it ideal in texturizing agents in food. It's got a pleasant, cool, sweet flavor, acts as a humectant, keeping foods from losing moisture because it absorbs the moisture. Okay. There's no acceptable daily intake has been specified for sorbitol that is considered to be very safe food additive. Okay, there's no limit to there's no limit by the FDA what you can take of it and be safe still. Okay. Ingestion of more than 50, 80 grams a day may have a laxative effect. If you ingest more than that of sorbitol. Okay. Mannitol. Okay. A structural isomer of sorbitol. Remember what structural isomer is? Structural isomer, same molecular formula, different structural formula. So it's a structural isomer of sorbitol. It's in asparagus, olives, pineapples, and carrots. Okay. For use in the food industry, it's extracted from seaweed. That's where you get mannitol from. It's got a little more than sorbitol, about 0.7 times sweetness of sucrose, and only about 1.6 calorie per gram. Xylitol, discovered in 1891, has been used as a sweetener since the 1960s. It's found in many fruits and vegetables, about the same sweetness as sucrose, but only 1/3 of the caloric value of sucrose. Okay, it's also got a high cooling effect because it absorbs heat during metabolism. When it breaks down, it absorbs heat, so it's a high cooling effect, and it's a sweetener. Contributes to its popularity as a sweetening agent in hard candies and gums, as well as in oral health products. A lot of dental chewing gum products use xylitol instead of sucrose. Extensive study says that use of xylitol, okay, between meals results in 30 to 60% decrease in dental cavities. So if the xylitol is not metabolized by bacteria to produce lactic acid, so you're not getting the dental caries from it. Okay, so polyols, multiple OH groups, give us sweetness that we enjoy without all the calories, cavities, and blood sugar peaks of sucrose, but they're not without negative side effects. Okay, some studies reported weight gain by individuals who overeat these sugar-free foods. Okay. One of the biggest ones is diet product, like Diet Coke, Diet Pepsi. That people who drink those a lot, extreme weight gains. Okay. Just because it's sugar-free does not mean you're going to have no weight gain with it. Okay, you see a lot of individuals that drink these diet drinks. That's an indication that is one of the things that causes weight gain in a lot of diets. American Diabetes Association reported that these foods are acceptable in moderate amounts, but should not be eaten in excess, just like anything else. You don't do it in excess. Some diabetics have suffered elevated blood glucose after eating foods containing these polyols. So it has the same blood sugar raising effects as sucrose. When ingested in excess, sugar alcohols may cause bloating and diarrhea. Okay, so here's what this is what sucrose looks like. Sucrose is 2 glucose molecules adhere together. Okay, mannitol, sorbitol, xylitol, and erythritol. Okay, are all sugar substitutes. But look at the OH groups. They're all polyols. That's what gives it the sweet flavor, all those OH groups, all those alcohol groups. Okay, on all of these. Same thing with sucrose. You can see the OH groups. That's what gives it its sweetness. There's some interesting facts. Acids and sugars. Okay, what soft drinks are. And if you look at some of these, pure water, pH of 7 means it's neutral, right? So here's your pure water, has a pH of 7. If you look at battery acid is, where's my battery acid down here? I want to print. Oops, hit the wrong button. There we go. Battery acid is pH of 1. Pepsi, okay, 2.49. It's 1 point above battery acid. Coca-Cola, 2.53. Okay, extremely acidic. It dissolves teeth. You take a baby tooth that a kid's lost, you put it in Coca-Cola, about 7 days it disappears. Okay, completely acidic. If you want to, one of the things we use it for is if you have a hitch on a car and it's rusted shut, pour Coca-Cola on it. Let it sit for a little while, you can break it right off. The acid dissolves the rust. Also dissolves the frame and everything else. But you look at some of the pH of these groups and it's amazing what they have in it. So Coca-Cola has 9.3 teaspoons of sugar at 2.53 pH. Diet Coke, Diet Pepsi. But look at Minute Maid orange soda, 11.2 tablespoons of sugar and 2.8 acid. Okay. So these drinks have tremendous amounts of sugar in it and very high acidic content. Okay, look at, and here's your Diet Coke. Diet Coke again, 3.39 pH. Nestea iced tea. Okay, 3.04 pH and 5 tablespoons of sugar. So you look at these, it's amazing how much sugar is in all the stuff that we drink. Physical properties of alcohols, more chemistry stuff. So ROH has a structure very similar to water. Hydroxyl groups are very polar. So hydrogen bonds can form readily. So high boiling points relative to their molar mass due to the ability to hydrogen bond. So when you have an ROH group, remember oxygen is more electronegative than hydrogen. So it pulls electrons towards. You get delta minus and you get delta plus. This just means delta means small charge. So the hydrogens are positive charge, the oxygens are negative charge. Opposite charges attract. So the oxygen of one alcohol attracts to the hydrogen of the other. The hydrogen of one alcohol attracts the oxygen of the other. And it makes these hydrogen bonds between the molecules. This allows a cohesive effect, pull those together. Okay, that's called hydrogen bonding. It's a weak bond compared to covalent or ionic bonds, but it's a strong bond compared to other intermolecular forces. Remember, we talked about intermolecular forces, those are between molecules. Intramolecular are within the molecule, like covalent or ionic bonds. So it is a strong intermolecular force. Okay? It allows for, you ever see those little bugs that walk on top of the water? That's because of hydrogen bonding. The water sticks together. They can walk on the water. You ever skip a rock on a lake? Okay, the only reason you can skip that rock is because of hydrogen bonding. The water molecules hold together and make a cohesive force. So when that rock hits it, it bounces off. Try skipping a rock on gasoline. You know, fill a pool of gasoline, skip a rock, it'll sink every time. Well, don't actually fill a pool of gasoline. Don't say a chemistry teacher told you to do that. Okay, but if you take a container of gasoline, you cannot skip a rock across it. It will sink. There is no hydrogen bonding. They're non-polar molecules. So it allows for the cohesive force of water and gives water some a lot of its properties. And it makes for a higher melting point because it holds it together harder. Okay, so hydrogen bonds form very readily with polar charges. So high boiling points relative to how big the compound is due to hydrogen bonding. So a hydrocarbon with the same molecular weight as an alcohol, which would have a higher boiling point. The alcohol will, right? Because of the hydrogen bonding. Okay, so it has hydrogen bonding, holds the other, so it has a higher boiling point than any other hydrocarbons. Okay, so alcohol boiling points. Alcohols have abnormal high boiling points relative to their size because of hydrogen bonding. That pulling of the oxygen pulls the electrons towards itself to give you a negative charge, hydrogen a positive charge. Okay, this is ethanol. Okay. You can see this is a negative charge. This is a positive charge. This is a negative charge. This is a positive charge. Opposite charges attract, and it pulls the molecules together and holds them together. That's what hydrogen bonding is. Hydrogen is very important in DNA. What forms our double helix structure of DNA is hydrogen bonding. Okay, it allows the base pairs in each DNA strand to pull together and form that double helix. And that is all because of hydrogen bonding. Hydrogen bonding causes a lot of our molecules to fold in the shape of a three-dimensional structure, okay, which allows our enzymes to function. So hydrogen bond is extremely important in biological systems. Okay, and this is all it is. It's when a hydrogen is attached to a very small, highly electronegative element, like oxygen. Okay, so let's look at this here. We have who wants to name this compound? You should be able to name this one by now. Anybody want to speak up?
Propane.
Propane, perfect. This is propane. This is dimethyl ether. We haven't done that yet. This is an ether. And this is ethanol. Remember, we take the ethane, drop the E, and add OL for alcohol. Okay. So this is the order of your boiling points. This would have a very low boiling point. Come up, there's no bonding here. This has a little bit of bonding because the oxygen has a little bit of a negative charge, nothing like hydrogen bonding. And this one has hydrogen bonding. So this is going to have your highest boiling point right here. Then it's going to be the dimethyl ether, and then it's going to be propane. Okay. When you have polar charges, it pulls things together because opposite charges attract. Get rid of the. So the boiling point of propane is minus 40 degrees centigrade. Propane is a gas. You have propane canisters at your house for barbecues, right? So propane is a gas. It's at room temperature stuff, it's already into a gas phase. Ethanol, you know, is not a gas because you drink it. You know, vodka, rum, scotch, whatever you have, that's ethanol. That's not a gas. Okay. It's not a gas because of the hydrogen bonding. It's the same molecular weight as propane. Okay, but you have that hydrogen bonding that holds it together. Okay. Boiling point of ether is minus 23, and the boiling point of ethanol is 78.5 degrees centigrade. Okay. Big jump because of the hydrogen bonding. Now notice, what's the boiling point of water? 100 degrees centigrade, right? So notice the difference between ethanol and water. That's how a still works. Okay. When you have a distillation of something. Oops, I lost my picture here for some reason. There we go. Okay. When you set up a still. Okay. What's going to boil off first? The ethanol or the water? Ethanol. Ethanol boils at 78.5 degrees centigrade. Water waits to 100 degrees. So if you control the temperature to roughly 80 degrees centigrade, you're going to boil off all the alcohol. It's going to run through all those condensing tubes and come out the other end. And it's going to come out a lot stronger, a lot higher concentration of ethanol because the water is being boiled off. The ethanol is being boiled off and being recollected as ethanol with no water mixed in with it. That's how it just to work. That's how moonshine works. Okay, that's how you make moonshine. You boil the water, you boil the ethanol mixed with water, your vodka, okay, and you run it through the distiller and then the condensing tubes, and that comes out as almost pure ethanol on the other end. Extremely strong drinks. Okay, my son didn't believe me when we were in Croatia, and we went to this farmhouse in these back roads. We were driving through these 4-wheel drives, and this guy had some moonshine. He made up his bathtub upstairs. And my son was 18, 17 years old, knows everything. And the guy brought out the moonshine. And I says, don't drink it like you do drink United States. I said, if you take a sip of that, it's not going to be the same. And of course, Dad doesn't know anything. So he took a big sip of it. Man, he fell back, his eyes watered. It was funny to watch him. But yeah, this stuff is really strong. Okay, but that's how you make moonshine right there, because of this difference because there's a difference in boiling points of ethanol and water. Okay, they all have similar molecular weights, 44, 46, 46. So the only difference is this oxygen group. It's an oxygen makes it a little bit, but that OH group allows for hydrogen bonding. Okay, which two are isomers? Look at those two up there. Look at all three. Which two of those three are isomers? That's a good test question too. You should know this one.
The ethanol and the ether?
Perfect. The ethanol and the ether. These are both isomers. Okay. They both have the formula C2H6O. This one does not have that same molecular formula. Both those have the same exact molecular formula, but they're different structures. One's an ether, one's an alcohol. Okay, but they're structural isomers of one another. Remember the definition of an isomer: same molecular formula, which is this, different structural formula. Okay, so here we have butane, and we have one propanol. Okay, propane with an OH group. The E is dropped, OL. And the one tells us what position this OL group is at, just like the rest of organic chemistry. Okay, tells us right what we got. Molecular weights are very similar. This has a boiling point of 0.5 degrees centigrade. Okay, it's a, okay, that's what it boils at. Boiling point of propanol is 97.2 degrees centigrade. Big difference. They both have the same molecular weight, roughly. Okay. But here you have hydrogen bonding. Hydrogen bonding is that very strong bond that holds them together, so they don't pull apart with heat as easily. So their boiling points increase tremendously with hydrogen bonding. Okay. Solubility of alcohols. Okay. Alcohols are polar. So low molecular weight alcohols are going to be very soluble, just like water. Okay. Like dissolves like. They're going to be soluble in water. So alcohols with 1 to 4 carbons are soluble in water. Okay. So methanol, ethanol, propanol, and butanol. 1 to 4 carbons are soluble in water. They're very polar. Hydrogen bond with water molecules. They dissolve within the water molecules. And they're hydrophilic. Hydrophilic means water loving. Hydrophobic means water hating. Okay, so they're very hydrophilic. As the number of OH groups increases, the polarity and solubility increases. The more you have hydrogen bonding, the more polar the compound is going to be, and the more it's going to dissolve in water. The more OH groups you have. So if I have, let's see, 1, 2, 3, 4 carbons with OH groups on both ends, that is going to be very soluble in water. Because you have 2 OH groups of hydrogen bonding. And it's going to hydrogen bond with the water molecules, because water molecules do hydrogen bonding also. And do the same thing with this, in this case, it's a butane diol. Okay. High molecular mass. As it becomes more and more carbons, as your mass increases, the alcohol becomes insoluble in water because the hydrocarbon part takes over. If you have a fatty acid, well, a fatty acid that's been reduced, all those carbons, and let's put an OH group at the end, okay? You're still going to get some hydrogen bonding, but this huge part, okay, all those carbons are going to be nonpolar. So that's going to outweigh this 1 OH group. Now, if I put on 3, 4, 5 OH groups, then it's going to start to be polar. Okay. Okay. It's still polar, but not as much as with a small amount of hydrocarbons. Okay. The ratio of hydroxyl groups to carbons determines your solubility. So how many OH groups you have to how many carbons you have determines solubility. Okay. If you got a 1-to-1 ratio, it's going to be very soluble. A 1 to 4 ratio is going to be soluble. A 1 to 20 ratio, it's not going to be soluble. 1 OH group to 20 carbons, not going to be soluble. If I start putting more OH groups on there, if I put on 5 OH groups to 20 carbons, that's 1 to 4. That's going to be soluble. Does that make sense? So the more carbons you have, the less soluble it's going to be. Okay. Diols and triols, which means 2 OH groups and 3 OH groups, are more soluble with only a single OH group. Alcohols that have 7 or more carbons to a single OH group are insoluble. Okay, so this compound here would be insoluble, would not be soluble in water. It's more than 7 carbons and there's 1 OH group. As the hydrophobic portion increases, the solubility decreases. The hydrophobic portion is the part that is non-polar, does not dissolve in water. It's water hating. So it's the carbon chain. So as that carbon chain increases, the solubility decreases because it takes up more of the molecule than the OH group. Okay. So intermolecular hydrogen bonds are attractive force between 2 molecules. Again, we're talking about intermolecular. Intermolecular means between molecules. Intramolecular hydrogen bonds are attractive force between polar groups within the same molecule. So the molecule can fold on itself, and it's intramolecular. The bonds are within the same molecule. That's what you get with some of our enzymes and some of our bases in the body that fold upon themselves. Okay, those are intramolecular, within the same molecule. So inter is between, intra is within. Okay, that's the difference. So an increase in the number of hydroxyl groups along a carbon chain will also increase the polar hydroxyl group. The more hydroxyl groups you're going to have, the more polar it's going to be. Okay. So diols and trials are more water soluble than alcohols with only a single hydroxyl group if they're the same size. If they're the same size and you have one OH group, or you have two OH groups or three OH groups, the three OH groups get more soluble than the two OH groups than the single OH groups. So diols and trials are always more soluble than alcohols with only a single hydroxyl group of the same size, same number of carbon atoms. Okay. So the presence of polar hydroxyl groups in large biological molecules keeps proteins and nucleic acid, allows intramolecular hydrogen bonding, keeps these molecules in shape for their biological function, like insulin. Insulin's produced, with chain folds on itself, hydrogen bonds intramolecular hold the shape of insulin. Okay, the shape of insulin allows insulin to work on the receptors. Okay, that allows sugar to be absorbed and get it and reduce the amount of sugar in the bloodstream and put it into storage. Okay, and that's because of the shape of the molecule being held together by intramolecular hydrogen bonding. Classification of alcohols. All right, alcohols, depending on the number of alkyl groups attached to the carbonyl carbon, are classified as primary, secondary, tertiary. Okay, just like our carbons. Remember, we had all these compounds with primary, secondary, tertiary carbons. A primary carbon has one alkyl group attached, secondary has two, tertiary has three. Same thing for alcohols. The carbon that has the OH group attached, if it has one carbon attached, it's primary, two is secondary, three is tertiary. So the carbonyl carbon is the carbon that has the hydroxyl group. Okay, so if we had carbon, 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 and we had an OH group, this is a carbonyl carbon. Okay, so it depends on the number of alkyl groups attached to the carbonyl carbon, attached to this carbon, not any of the others. It's the one that has the OH group attached. That's your carbonyl carbon. Okay. So methyl alcohol, that doesn't even qualify because it doesn't have any carbons attached. Okay. A primary alcohol has one alkyl group attached. A secondary alcohol has two alkyl groups attached. A tertiary alcohol has three R groups attached. Okay, and this will be very important in the reactions because they react differently. Certain primary and secondary alcohols can react, and where tertiary ones cannot because there's no hydrogen on them. Okay, so this is methyl alcohol, which is methanol. So one carbon, four hydrogens, and one alcohol right here. There's your OH group. This is ethanol. Ethanol is a primary alcohol. It has two carbons. Here's your carbonyl carbon, carboxyl carbon, and it has one carbon attached right there. And that's ethanol. 2-propanol. 2-propanol means three carbons is propane. Okay, all single bonds, AN, OL means there's an alcohol at the number 2 carbon. So this is what it looks like. Here's your carbonyl carbon right here. How many carbons are attached to that carbon? There's 2. It's a secondary alcohol. And this is 2-methyl 2-propanol. Again, when we write these things out, we'll do a little bit of practice, but always work backwards. We have an OL group, which means we have an OH group on there. OL, it says. Propane means there's 3 carbons, all single bonds. The OH group is the number 2 position. So here's your OH group at the number 2 position. At the number 2 position, there's a methyl group also. So this is a carbonyl carbon. There's 1, 2, 3 carbons attached. 3 carbons attached to the carboxyl carbon gives it a tertiary alcohol, makes it tertiary alcohol. So know the difference for your exam between primary, secondary, and tertiary alcohols. Okay. So classify the alcohols. Okay. Is letter A primary, secondary, or tertiary alcohol? Someone take a guess.
Secondary?
What was that?
Secondary?
Secondary, perfect. This one's a secondary alcohol. It has 2 carbons. Here's your carboxyl carbon. It has 2 carbons attached. Okay. Next one. Is it primary, secondary, or tertiary?
Which one's the next one? The one to the
Oh,
right
I'm
or the
sorry.
one at the bottom?
I'm sorry. Let's go this way. You're right. Let's go to the right.
Primary.
Primary, perfect. Has 1 carbon attached to the carboxyl carbon. Okay, let's go down to this one here.
Tertiary.
Tertiary, perfect. And let's go to this one here. Last one.
Should be secondary.
We have secondary. There's 2 carbons attached. That is perfect. Okay, then you remove the little dots we made, and we'll go through each one, but that's exactly right. Okay, it shows you 2 carbons attached to that carbon. So the carbonyl carbon has 2 other alkyls attached. It is secondary, just like we said. The next one, this one we're getting down this time. Here's your carbonyl carbon, has 3 carbons attached. Okay, it is tertiary. Next one, C, has 1 carbon attached. It is primary. Okay, that's them right there. And D, this has 2 carbons attached to that carboxyl carbon, and it is secondary. Okay. So you all should be able to identify primary, secondary, and tertiary alcohols now. 2 alcohols distribute to the distinct flavor of mushrooms. Okay. They are 1-octanol and 3-octanol. Draw the line structures of these 2 molecules and provide their common names. Classify the alcohols as primary, secondary, or tertiary. So 1-octanol. Okay. How many carbons does 1-octanol have?
8.
8.
So draw the line, the line structure. 1, 2, 3, 4, 5, 6, 7, 8. And at number 1, there's a what? OH group. Because octanol means an alcohol. Number 1 position, 8 carbons, all single bonds. That's the line structure. Okay. That's a little bit better line structure. It's not as fancy as that one. But 8 carbons. I'm sorry, other way. 1, 2, 3, 4, 5, 6, 7, 8. Remember, you always give the functional group the lowest possible number. Okay. Is that a primary, secondary, or tertiary alcohol?
A primary?
A primary, perfect. Okay, it's octanol alcohol, and it is a primary alcohol. Okay, 3-octanol. Same thing, you're going to draw 8 carbons. Okay, 1, 2, 3, 4, 5, 6, 7, 8 carbons. And at number 3, we're going to put what? What do we put at number 3 there?
OH group.
An OH group, perfect. It says it right there. Octanol is octane, 8 carbons. AN means all single bonds. OL means there's an alkyl group. And this tells you what number it's at. Alcohol is just an OH group. Okay. So get rid of some of these lines here I put in there. Okay, so here's your OH group and is at the number 3 position. This was your OH group at the number 1 position. Okay. And this is 3-octanol alcohol. And what is it? A primary, secondary, or tertiary alcohol?
Secondary.
That's a secondary. Secondary alcohol. There's 2 carbons attached to the carboxyl carbon. Okay. Classify each of the following alcohols as primary, secondary, or tertiary. What is this one?
Secondary.
Secondary. Secondary alcohol. Perfect. What is this one?
Tertiary.
Tertiary. Perfect. I think you guys got this. And this one.
Primary.
Primary. Perfect. Okay, classify each primary, secondary, tertiary, or aromatic phenol. Remember, we talked about you can have phenols also. A phenol is, remember phenols, phenol is benzene ring, conjugated double bonding system with an OH. Those have a different naming system than the primary, secondary, tertiary because they have conjugated bonding systems. Because remember, I told you this, it's not a single bond and double bond, it's a hybrid. Every one of those bonds is 1 1/3 of a bond spread out evenly. So you can't have a secondary, primary, tertiary because the carbons aren't shared evenly around it. Okay, so it's an aromatic or phenol compound if it has a benzene ring with the OH group. So we either have primary, secondary, tertiary, or aromatic, which is our phenols. All right, so A, primary, secondary, tertiary. What do we think? Primary. You got it. Who wants to name that alcohol?
Butanol.
Perfect. 1, butanol. Okay, butane, 4 carbons, AN single bonds, OL ending. Number 1 is where the OH group is attached. So 1 butanol. All right. Primary, secondary, tertiary.
Secondary.
Secondary, perfect. Okay, it's got 2 carbons attached. Name this one.
Three pentanol.
Perfect. 3, pentanol. 5 carbons, has an OH group attached at the number 3 position. So 3 pentanol. And this one, primary, secondary, or tertiary.
Tertiary.
Tertiary. There's 3 carbons attached to that bond. Now, who wants to name this one? I'll give you a little bit to look at it. You should be able to name it though.
Two methyl 3 pentanol. Or 2
Oh.
pentanol.
Cyclopentanol. There's 5 carbons in a ring. So it's actually, this is a number 1 position here to give the OH the lowest number. So it's 1 methyl, 1 cyclopentanol. So it'd be 1 methyl, 1 cyclopentanol. So it tells you it's an alcohol. It tells you it's cyclopentane, which is a 5 carbon ring structure. Number 1 is the OH position. And at number 1, there's a methyl group attached too. So 1 methyl, 1 cyclopentanol. Perfect. All right. Primary, secondary, tertiary, or aromatic.
Aromatic.
Aromatic has a benzene ring. It's aromatic or phenol. Aromatic phenol are the same thing. And that's named as phenol. And primary, secondary, tertiary.
Secondary.
Secondary, perfect. There's 2 carbons attached to it. And let's name that one. The same thing as the last one, except there's no methyl group.
1-cyclopentanol.
Perfect. Perfect. 1-cyclopentanol. All right, now we're going to name these things, start practicing with them. That was just for giggles. All right, the IUPAC, based on the longest carbon chain containing the OH carbon. So when you have a function, but that's off on the screen. Okay, pins are making it's kind of off on the marks here. All right, longest carbon chain that contains the OH group. The E of the alkane group is replaced with OL. Man, how do I get so far off on this? I'll have to adjust something. Now let's try it again. There we go. It just got off. Okay. We're back on track. So you drop the E and add OL for an alcohol. Okay. The carbon is numbered from the end giving the OH group the lowest numbers. Okay. So far we've had substituents get the lowest number. Then we had multiple and triple, we had multiple bonds get the lowest number that took place over substituents. And now functional groups is the lowest number, which takes place over the multiple bonds or the substituent groups. Okay, so if you have a functional group, like an OH, a carboxylic acid, a ketone, anything like that, if you have a functional group, that takes precedence over a double bond, over a triple bond, and over substituents. Okay. So you have substituents and a double bond, the double bond takes precedence. If you got substituents, double bond, and a functional group, the functional group takes precedence of what gets the lowest number. So any functional group is always going to get the lowest number possible. The name is prefixed with a number indicating the position of the OH group. Depending what carbon number it is on, you have to tell us where it is. For cyclic alcohols, the OH is at C1. So if you got any kind of cyclical compound, like cyclopropane, okay? Wherever I put the OH group, this becomes a number 1 carbon right here. Okay, that's a number 1. Okay, so wherever the OH is in any kind of cyclical compound where the OH group is attached, that becomes a number 1 position because it's the lowest number. Okay. Alcohols with 2 or 3 hydroxyl groups are named diols or triols with a number for the position of each OH group. So it's 1,2 diol or 1,2,2 triol. Okay. So name the alcohols. Let's name this thing. Where's our longest carbon chain? Our longest carbon chain is right there. So off of it, we have a substituent group. We have an alkyl group, substituent group, and we have an OH group, a functional alcohol group. So which one of those 2 gets the lowest number? The OH or the CH3?
The OH.
Perfect, the OH. Okay. Are we going to number this from left to right or right to left?
Left to right.
We're going to number left to right?
Right to left.
Or are we going to right to left?
It's right to left.
It's right to left because of this, if I number left to right, this puts number 3 in my OH group. If I number right to left, this puts number 2 for my OH group. And you always want to give your functional group the lowest possible number. So we're going to name it right to left, and then we put our substituents on there. So let's see, we have how many carbons in our longest chain? We got 4, right? So it's butane, that's where I said down there. And we have an OH group attached. So it becomes butanol. We drop the E and add OL, and we tell it where it is, 3-butanol. So that takes care of this. And now we have a substituent group here, and that's at number 3. So it's 3-methyl, 3-butanol.
Wouldn't it be 2-butanol?
Oh, I'm sorry. It is 2-butanol. I don't know why I said that. It is 2-butanol. I still look at the number 3 right here where I wrote it. That's why I shouldn't have written that there like that. It is. You're right. It's 2-butanol. So it's 3-methyl 2-butanol. Okay, remember, dashes between numbers and letters, commas between numbers. So you name the parent compound. 4 carbons in the longest chain. That's butane. Replace the E with OL, you get butanol. You number to give the OH group the lowest possible number, so it's right to left. So it's attached to, the OH group is attached to C2, the methyl group is on C3. And that's how you name it. 3-methyl 2-butanol. Okay. The leafcutter ant uses chemicals produced in its mandibles to signal alarms to others. One such pheromone is 4-methyl 3-heptanol. Draw the line structure for this molecule. Okay, remember what I told you in organic chemistry? You always work backwards, right? So start at the back. So heptanol. Heptanol is how many carbons?
7.
7.
7 carbons. Are there double or triple bonds in it?
No.
No, because it's AN. The AN means all single bonds, and the OL is alcohol. So let's draw a line for 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. Okay. At number 3, there's an OL. There's an OH group on it. So let's go 1, 2. Let's count from this end. Then 3. There's your OH. And number 4, there's a methyl group. That's it. That's how to draw your line structure. That's 4-methyl 3-heptanol. Okay, that's a better picture down the computer. Okay, but you see this is number 1, number 2, number 3, and number 4. Remember, methyl group, you don't write the CH3 because any ending of a line is a carbon. So there's a carbon here, there's a carbon, and any bend is a carbon. So there's 7 carbons and a carbon on top. So that's 4-methyl 3-heptanol. All right, cyclical alcohols. Okay. So now we're going to name the cyclical compound. Remember, OH gets a number 1 position. So if this is 1, that looks like a 2 actually. I can't make a 1. Okay, there's our 1 position. So now, are we going to go 1, 2, 3, 4? Is it number 5 for the methyl group? Or is it number 3? We're going to give it the lowest possible number. So we're going to count this direction. Okay, not the other way. We'll go 2, 3. Because we went this other way, it would be number 5. 1, 2, 3, 4, 5. So we're going to count that direction. All right. So how many carbons do we have in the ring?
6.
6. So it's cyclo, hex, and they're all single bonds, ANO. And it's number 1 position. So 1 cyclohexanol. That tells us our OH group is at number 1. That tells us we have 6 carbons, all single bonds in a circle. And we also have a substituent attachment. We have a methyl group at number 3. So it's 3-methyl 1-cyclohexanol. Okay, the functional group is always a number 1 position on the cyclical ring. So you name the parent compound, which is cyclohexane. Okay, 6 carbons, ring structure, all single bonds. You replace, drop the E, okay, and add OL. So cyclohexanol. Okay, we're at the number 1 position of cyclohexanol, and we're going to go counterclockwise to give the methyl group the lowest possible number. Okay, so the OH group must be at C1. Anytime you have a cyclical structure, the functional group has to be the number 1 carbon. That's the rules. Okay, name the substituents. You have methyl on number 3. So we have 3-methyl cyclohexanol. And you can put a 1 in there, or you can leave it off. It's still the same thing because it has to be in their own position. I would not mark it wrong either way. You put 3-methyl cyclohexanol or 3-methyl 1-cyclohexanol. They say the same thing. Okay, name the following alcohols. Okay. Again, name the root. What's the ring? Cyclo what?
Hexanol.
Cyclohexane, hexane. Drop the E and add OL. You're right. Cyclohexanol. Okay. This has to be the number 1 position by definition. So what position is the bromine at?
3.
3. Perfect. So you would have 3 bromo, 1 cyclohexanol. Okay, that's how you would number it. There's 6. So 3 bromo cyclohexanol. You can put the 1 in there or not. Either way is fine. Okay. Name each of the following compounds. All right. Let's take a look at this one. Go about another 10 minutes. Take a 10-minute break or so. All right. Use our nomenclature to name each of the following compounds. So, how many carbons do we got? 1, 2,
5.
3, 4, 5 carbons. Okay, so what is it?
Pentanol.
Pentanol. Perfect, because it's pentane, drop the E, add OL. We give the OH group the lowest possible number. So are we going to count left to right or right to left?
Right
Which
to
one?
left.
Right to left. So this is going to be number 1, number 2, number 3, number 4, and number 5. Because this has to have the lowest possible number. And we have a substituent group at number 4. So we have, so putting all this together, what's the name of the compound?
4-methyl pentanol.
Perfect. 4-methyl 1-pentanol. Methyl 1-pentanol. Okay, 4-methyl pentanol or 4-methyl 1-pentanol. Okay, again, if there's no number, we assume it's at number 1. All right, name this thing. 1, 2, 3. How many carbons in our longest carbon chain?
6.
It's 6. Our longest carbon chain runs just like this. Okay. It's not always in a straight line. So we have an attachment here. And we have our functional group here. So are we going to start numbering from the left side or are we going to start numbering from the right side?
Right.
Left.
Perfect. Start from the left. That'll give you the lowest possible number to your OH group. 1, 2, 3, 4, 5, 6. All right. So let's put everything together. What is 6 carbons with an OH group attached. 6 carbons is
Hexanol.
hexanol. Okay, where's the OH group?
At 2.
At number 2, so 2 hexanol. And the methyl group is at what number? Number 4, right? There's your methyl group right here. It's attached to number 4 carbon. Okay, so put together is 4 methyl, 2 hexanol. Okay, you break the name down, it says everything is in it. There's hex is 6, all with long chain. AN is all single bonds. OL is OH group at number 2. Methyl group, we add at number 4. Everything's written right in the name. Just break it apart, always read it backwards. All right. That's interesting. So what do we got there? Someone want to guess here? Okay. How many carbons?
3.
3. So it is pro, pan, O. And where's the OH group?
1, 2,
1, 2, and 3, right? Perfect. So we got 1, 2, 3. Propane, tri, O. 3 OL, which is our OH groups or alcohol. So trialcohol. Pro is 3 carbons. AN is single bond. And they're within 1, 2, and 3 position. So 1, 2, 3 propane triol. Okay. And there's another one here. So longest carbon chain is how many?
Six.
Perfect. There's 6. Okay. So are we going to number the chain from right to left or left to right?
Right to left.
Right to left. Perfect. Okay. So there's 6 carbons. So this is hexane, and drop the E, put an OL, and that's at the number 1 position. So 1 hexanol. That takes care of this here. Then we have attachments on this. We have number 1, number 2, number 3, number 4, number 5, number 6. So at 3, what kind of attachment do we have?
Methyl.
Methyl. At number 4, what attachment do we have?
Chloro.
Fluoro. And you put it together. So what comes first in this name?
Chloro.
Chloro, because it's alphabetical. So we end with 4 chloro, 3 methyl, 1 hexanol. 4 chloro, 3 methyl hexanol, or 4 chloro, 3 methyl, 1 hexanol. Okay. Again, we're writing compounds. Make sure you put commas between numbers and dashes between letters and numbers. Common names of alcohols. It's not bad if we have to do the IUPAC. The exam will only test you on the IUPAC names. Common names, you just like rubbing alcohol or things like that, or ethyl alcohol. If you know the IUPAC name, that's what the exams will be on, because that's a universal system. But we do have some common names. This is tert butyl alcohol, because here's a tert butyl group. Remember tertiary butyl? Tert is 4, butyl's 4 carbons. Tert butyl is a tertiary, 3 carbons attached. So it's tert butyl alcohol. What's the real name of the alcohol, the IUPAC name? That's the name I want you to know for the test. Someone give me the IUPAC name for that thing.
Methyl 2-propanol.
You got it. Perfect. 2-methyl 2-propanol. I was going to say, yeah, 2-methyl 2-propanol. That's the IUPAC name. Propanol, you have 3 carbons. You have an OH group at number 2. You have a methyl group at number 2. Okay. The next one over to the right is isopropyl alcohol. This is your rubbing alcohol. This is you get in the stores. You know, what's the IUPAC name for this thing?
2-propanol.
Perfect. 2-propanol. I mean, you walk into Rite Aid, ask for 2-propanol, they kind of look at you funny. You ask for isopropyl alcohol, they'll give it to you. But it's the actual IUPAC name is 2-propanol. Okay. So the combination for alcohol is just the alkyl name, a space, and the word alcohol. That's how they do it. All right. Again, common names of alcohols. Common name is this is going to be ethyl. This is ethylene glycol. Okay. Or what's the IUPAC name for this?
1-propanol. Oh, wait, no, that's 2. Ethanol. So 1 and 2 ethanol.
One, almost. What do you put in front of the OL? If there's 2.
Bi.
Bi, perfect. Okay. 1,2-ethane diol. There you put the di. It's di if there's 2, it's tri if there's 3. So it tells you at the 1 and 2 position, ethane group, there's 2 carbons, all single bonds, and there's 2 diols. So 1,2-ethane diol is the IUPAC name. We'll do this and then we'll take a break. All right, what do we got here? This one we should all know. You drink this every weekend.
Ethanol.
Ethanol, perfect. And it's ethyl alcohol, or the IUPAC name is ethanol. Draw structures for each of the following alcohols. 2-methyl 1-propanol. Okay, so we always work backwards, right? Okay. So propane is how many carbons? We can dissect the name here. 3, perfect. AN means what?
All single bonds.
Oh, single bonds. OL means
Alcohol.
alcohol. Perfect. OH group at number 1. And then we have number 2, we have a methyl group. So that's what it is. You have 3 carbons. So let's put 3 carbons. We got an OL group at number 1. Let's make this number 1 over here, which is fine. So OH, all single bonds. And then at the number 2, we have a methyl group. So this is CH3, CH, CH2, OH. And that's our structure. Okay. Number 1, we have our OH group. At number 2, we have our methyl group. And we have 3 carbons, all with a single bond. 2-methyl, 1-propanol. Okay. 2-chlorocyclopentanol. Okay. So we have a cyclopentene. So we have 5 carbons in a circle. Okay. There's 5 carbons. And it's an OL. And whenever we have a cyclical compound and we have an alcohol, the functional group is always number 1. So no matter where I put the OH group, this is number 1. Okay, no matter where it is. So this is cyclopentanol right here, all single bonds, cyclical 5 carbons. And then at number 2, there's a chlorine group. I could put it here, or I could just as easily put it right there too. Would have been the same compound because you roll in 3-dimensional space, it's the exact same thing. Okay. So this is our number 1. There's our number 2. So 2-chlorocyclopentanol. Okay. 2,4-dimethylcyclohexanol. So cyclohexanol is how many carbons in a circle?
6.
6. Perfect. So 6 carbons in a circle. Okay. So cyclohexanol, let's make this number 1. By definition, we put our OH group there. That's number 1. So dimethyl, 2,4-dimethyl, so that's cyclohexanol right now. And at number 2, and number 4, there's a methyl group. So 2,4-dimethyl cyclohexanol. Yeah, let me get rid of my drawing there. That one's a little bit better. Okay. So cyclohexanol, 6 carbons. By definition, OH group is always number 1, 2, 3, 4, 5, and 6. So 2,4-dimethylcyclohexanol. 2,3-dichloro-3-hexanol. Right. So hexanol is how many carbons?
6.
Let's do the line structure. 1, 2, 3, 4, 5, 6 carbons. So there's hexane. All single bonds. An OL group, which is an alcohol, at number 3. Okay, so there's 3 hexanol right there. And at 2 and 3, there's 2 chlorine groups. So at 2 and at number 3, there's chlorine groups. So 2,3-dichloro-3-hexanol. Okay, there's it outside, not in the line structure, but there's the structural formula of it. Same thing. This is number 1, 2, 3, 4, 5, 6. So there's hexane. At number 3, there's an OH group, which we got right here. And at 2 and 3, there are chlorine groups. So 2,3-dichloro-3-hexanol. Give the IUPAC name and the common name for each of the following compounds. Okay, how many carbons? A bunch. I count. Anyone else count 7? Okay, 7 carbons. So 7 carbons is?
Heptanol.
Heptane.
Heptanol, right? It's heptane, it's 7 carbons, perfect. Drop the E, add OL, heptanol. That's it. Heptanol or 1 heptanol. Okay. Common name, and so it would be heptanol. Common name would be heptyl alcohol. You name it like an attachment. Like I said, concentrate on the IUPAC name. That's when we're going to be using everything to identify. All right, IUPAC name would be what? Who wants to name this thing?
Propanol.
Perfect. 2 propanol. Okay, 3 carbons. Number 2 position. OL ending. So 2 propanol. Okay. And isopropyl alcohol, because this is isopropyl right here, that group. Okay, that was interesting. Let's name this thing. Okay, what's the main compound here?
Hexanol.
Hexanol. And what goes in front of the hexanol? all-
Then 1.
Right, but it's what? It's what kind of structure?
Cyclo.
Oh, cyclo.
Cyclo, perfect. Cyclohexanol. So this is cyclohexanol. And you can put number 1, number 1. This has to be number 1 carbon. Okay, because the functional group has to be number 1. So then we give the lowest possible numbers to the substituent groups after the number one for the functional group. So 2, 3, 4, 5, and 6. So we got bromines at 2 and 4, right? So we got 2, 4 di bromo. And we got a chlorine group at number what? 3? 3 chloro. So what comes first, the dibromo or the chloro?
Bromo.
The bromo, right? Because the di doesn't matter when doing alphabetical order. This is what counts for alphabetical order, the groups. So it'd be 2, 4 dibromo, 3 chloro, 1 or just cyclohexanol. 2, 4 dibromo, 3 chloro, cyclohexanol. And you can see how these can get really long if I start putting all kinds of funny things on them.
You want to put a 1 in front of the cyclo or no?
You can either way.
Oh,
Because
so,
yeah, whenever you have a cyclical compound with a functional group, the functional group is always given the number one position, no exceptions.
okay,
So if there's nothing, it will not be marked wrong if you put one cyclohexanol at all.
okay.
It's the same exact thing, but you can put it or not put it. Either way is fine. Because by definition, once you have a functional group on a cyclical compound, that's the number one position.
Okay.
It's by definition. Oh, the common name is 2,4-dibromo 3-cyclohexyl alcohol. This gives a space there. It's only going to be the common names. All right. So let's name this thing. What's our main name here? What's the longest carbon chain?
Cyclopentanol.
Cyclopentane, right? Or cyclopentanol. Perfect. So this is a cyclo. Pentan. Oh, that's this one right here. And are we going to go to the left or are we going to the right when we number?
Doesn't matter.
Makes no difference. Either way, it's going to be 2, 5, 2, 2, 5. No matter which way you name it. Okay, no matter which way we go, because this is number one, no matter what. And this could be 2, or that one could be 2, 3, 4, 5. Okay, so make sense which way we go. We're always going to have a 2, 5 di methyl. So we have 2,5-dimethyl cyclopentanol or 2,5-dimethyl 1-cyclopentanol. So 2,5-dimethyl cyclopentanol. And again, if you break it down, it tells you everything. Always read it backwards. It means it's an alcohol group and you got a cyclical compound with 5 carbons, all single bonds. So that goes in number one position once it's a cyclical compound. You have 2 methyl groups, 1 at 2, 1 at 5. Okay, it all makes sense. Just take it piece by piece, section by section, and break it down. And always read it backwards. Okay. Medically important alcohols: methanol, CH3OH, methanol. Okay, methanol is wood alcohol. Methanol is toxic. It will make you go blind. You ever hear the expression, keep doing that and you'll go blind? This is where it came from. Methanol is wood alcohol. It will make you go blind. During Prohibition in the United States, okay, they substituted methanol for ethanol. People were serious about drinking. Okay, instead of ethanol, they couldn't get ethanol, so they got methanol. Okay, methanol is toxic. People drank the methanol until their vision got blurry. Then they went in the bathroom and threw up to keep them from going blind. That's what they used to do during Prohibition. That's where the expression came from. You keep doing that, you're going to go blind. But it takes on many different names and many uses nowadays. Okay, but that's methanol. Methanol is extremely poisonous, very toxic to the human body. Okay, it's colorless and odorless, but it tastes like ethanol. It's used as a solvent because it's polar. It's toxic, can cause blindness and death if ingested. Okay, it can be used as a fuel. It's like any alcohol can be used as a fuel. You can burn it. Used as a starting material for the synthesis of formaldehyde. Formaldehyde is another toxin. Okay, formaldehyde is a preservative We use it in embalming, and it's also used in chocolate ice cream. You'll find formaldehyde. Okay, it is also known as wood alcohol. Okay, ethanol, one more carbon. Now we got something everybody can drink. Okay, odorless and colorless liquid. Okay, widely used as a solvent. Again, very polar. So things, polar compounds dissolve in it. It is the alcohol in alcoholic beverages, whether you're drinking scotch, bourbon, whiskey, brandy, vodka, whatever you're drinking, ethanol is the alcoholic part of it. That's the part that gets you the feeling, the buzz feeling. It is derived from fermentation of carbohydrates. That's how we synthesize ethanol. Okay. Beverage produced varies with the starting material and the fermentation process. So depending how we ferment it and what we use to start with gives us our different alcohols. That's kind of cool. Okay, so we have glucose, C6H12O6, that's our carbohydrate. We take enzymes with it and it produces ethanol plus carbon dioxide. That's why when you make alcohol, you have to burp the container every once in a while, let the gas out because you're producing CO2. If you don't let that out, you created a bomb. Whenever you have gas and you're making gas in a closed container, that's a bomb. It's going to give, something's going to give eventually. Okay, that's why you have to have the spout or safety valve, whatever, when you make that. Also, when you make champagne, okay, all those little bubbles in champagne, that's the CO2 that's been trapped in it. So all that is carbon dioxide coming out of it. Those are your bubbles in champagne, okay, or any alcoholic drink for that matter. So champagne, sparkling wine, fermentation is carried out in a sealed bottle. So it keeps the CO2 in place. That's why it bubbles. Under these conditions, carbon dioxide produced during fermentation is trapped in the wine. That's what makes it champagne. Ethanol used in alcoholic beverages comes from the fermentation of carbohydrates, like we said, sugars and starches. Okay. The beverage produced depends on what you start with and your fermentation process. So if you want to make scotch, you start with grain. If you want to make bourbon, you start with corn. If you want to make Burgundy wine, you start with grapes and grape skins. Okay. Chablis wines, grapes without the red skins. Make Chablis. And beer, malted cereal grains. Okay. So it's a class on how to make different types of alcohol. Okay. Depends what you start with, what your carbohydrates are, depends what you end up with. But all of them have ethanol as the alcoholic compound. Ethanol is the main in all of them. No matter what you start with, what you're making. All right. We have something called fetal alcohol syndrome, okay, which a lot of people did not know about in the past. But fetal alcohol syndrome, okay, is the use of alcohol beverages by pregnant women can cause fetal alcohol syndrome, FAS. Okay, a syndrome, any kind of syndrome, is a set of symptoms that occur and are characteristic of a particular disease. Like Down syndrome has specific facial features, different other types of mental abilities, things like that. Any kind of syndrome is a set of symptoms that all are characteristic of that disease. And they differ from person to person. With fetal alcohol syndrome, physicians have observed that infants born to women with chronic alcoholism show a reproducible set of abnormalities, including mental retardation, poor growth before and after birth, and facial malformations. Okay, those are the set of symptoms that all go together. So fetal alcohol symptoms are going to produce mental retardation, poor growth before and after birth, and facial malformations. Right? Mothers who report only social drinking may have children with fetal alcohol effects, a less severe form of fetal alcohol syndrome. So the syndrome is all the complications. Effect, I mean, if you have 1, 2, 3 drinks when you're pregnant, you can have fetal alcohol effects. You can have the same effects, but to a lesser degree, or not all the symptoms together. Okay, so this milder form is characterized by reduced birth weight, some learning disabilities. Okay, so reduced birth weight, some learning disabilities, and behavioral problems when the child grows up. Okay, that's fetal alcohol effect. So only social drinking will cause that, not alcoholism. How does alcohol consumption cause these very symptoms? What does it do? No one's exactly sure what it does, but it's well known that alcohol consumed by the mother crosses the placenta. So ethanol gets into the bloodstream of the fetus. Okay. That's the dangerous part. Ethanol crosses the placenta. Within about 15 minutes, okay, the concentration of alcohol in the blood of the fetus is as high as that of the mother. So when the mother takes a drink, she gets a certain alcohol level. In 15 minutes, that same alcohol level is in the blood of the child. The fetus is just as drunk. Okay, and it doesn't have all the organs to filter out the poison of the alcohol. Okay, the mother has enzymes to detoxify the alcohol in her blood. The baby doesn't. Okay, all that is toxic to the baby. Okay, there's no way to detoxify, because ethanol is a poison. But we have enzymes that detoxify, so we get a high, we get buzzed from whatever, and then it breaks it down, and you can get a hangover, stuff like that. But the baby doesn't have those enzymes. They're not developed. Okay, so the baby just got that pure alcohol in the system and can't get rid of it. Okay, consider that alcohol can cause cell division to stop or be radically altered. Okay, so what's that going to do with developing baby? It is thought that even a single night on the town could be enough to cause fetal alcohol syndrome by blocking cell division during a critical period of development. Okay. So we asked the question, how much alcohol can a pregnant woman safely drink? What do you think the answer is going to be?
None.
Very good, none. Okay, that's how much a pregnant woman can safely drink. You can't go out and say, well, only have 1 or 2 drinks, because you got to remember, it's not going to affect you the same way as affects the fetus. You can't break that down. And it's going to be the same levels you get within 15 minutes of drinking it. Okay. As we have seen, this various symptoms seem to increase with the amount of alcohol consumed by the mother. Okay. However, it's impossible to do to the scientific studies that will conclusively determine the risk of the fetus caused by different amounts of alcohol. We can't take a pregnant woman, give her 1 drink, take another one, give her 2 drinks, give her 3, and then see how the baby comes out. You can't do that. That's not ethical. Okay, you can't do experiments like that on people. That's not done, or it shouldn't be done. Okay, so you don't know, because we're not going to do those experiments to find out. Okay, there is some evidence that suggests there is a risk associated with drinking even 1 ounce of absolute alcohol each day, which is 100%. Okay, just 1 ounce of it. 1 ounce is not that much. Okay. Because of these facts and uncertainties, the American Medical Association and the U.S. Surgeon General recommend that pregnant women completely abstain from alcohol. That's just the logical thing to do, because you don't know how much is going to cause the effects that you see, whether fetal alcohol syndrome or fetal alcohol disease. Okay. The sale and use of pure ethanol, 100% ethanol, is regulated by the federal government. Okay, you're not buying drinks that are 100% ethanol. Okay, 100% ethanol is what's called 200 proof. So I think abstinence, I think it's like 180 proof. I think it's as high as you can get. Okay, 100% ethanol is 200 proof, is fatal if you drink it. And it's regulated by the federal government. We use it in labs and things like that. Okay, to prevent illegal use of pure ethanol, it's denatured. You ever hear the term denatured alcohol? We put an denaturing agent in, make it unfit to drink, but suitable for laboratory experiments. So when we use alcohol in the lab, you go back to lab, we use alcohol. We use denatured alcohol, which means you cannot drink it. It doesn't do good. Okay. We had I did research at Long Beach VA Hospital for 3 years, and in genetics and in different hormones. We developed what's called cortical androgen stimulating hormone, was the one we were looking for in rats. The person next to me had an alcohol permit for 100% alcohol. He had a $75,000 grant by the US government to get fish drunk. He would add pure alcohol to their water, and he'd sit there and watch the effects as they swim. 75 grand to get fish drunk and watch their effects. It was unbelievable. But that's what alcohol is. So when you use alcohol in the lab, it's 100% ethanol, and it's denatured. So denatured alcohol is not suitable for drinking. So don't think you can break into a chemistry lab and get some alcohol, because you can't drink that stuff.
Okay, but what were the results of his study? Because
Yeah.
No,
that
I don't. I think he drank more alcohol than fish. I don't think he ever had any. I really don't know, but he got fish drunk. He just watched them swim, and he got $75,000 to do it. I was amazed, absolutely amazed.
Maybe to just see if like, I guess like if you're dumping that stuff down the drain, and because we live in like areas like San Diego, they say like all the drain water goes straight to the ocean,
Yep,
like toxic for fish.
it could be. Well, it wasn't toxic, but he got him drunk. But still, most people aren't taking their alcohol down the drain. Most people are consuming it. I don't think that's a big problem. Most people don't flush their alcohol. Some people do, but most people drink it. All right, 2-propanol. Okay, 2-propanol is isopropyl alcohol. 2-propanol is CH2-propanol. There you go. That's 2-propanol, or just, there's the line structure. Okay, isopropyl alcohol. It's colorless, but isopropyl alcohol has a slight odor. You can smell isopropyl alcohol when you use it. Okay, it's commonly called rubbing alcohol. It's great for cleaning things, getting dirt and all the grime off. If you're going to use, what are the things you stick to your dashboard? You put your iPhones on it, you mount them, or cameras, something like that. Those little suction cups. If you clean it with that rubbing alcohol or isopropyl alcohol, they really stick a lot better because it gets all the grime and stuff off there when you clean with it. It's a good use for rubbing alcohol. It is toxic when ingested. Do not drink rubbing alcohol. Okay. It is used as a disinfectant, astringent, okay, stop bleeding, industrial solvent, because things will dissolve in it. It's polar. Okay. And 1,2-ethane diol. 1,2-ethane diol is antifreeze. So ethane is 2 carbons. Okay. Diol, 1 and 2. CH2, CH2. Okay. That's 1,2-ethane diol. That's ethylene glycol. That's antifreeze. Okay. Antifreeze is toxic. Okay. If you don't like coyotes coming around your house, put a little bowl of antifreeze out. They will drink it. Antifreeze tastes sweet. Look at the OH groups on it. It's a polyol. It's sweet. Coyotes will drink it and they will die from it. Now, children will drink it too, and they can die from it. So be really careful when you set it out. It is sweet tasting. A kid will drink it. Okay, and it is toxic. Okay. There is a disease, that's a way of getting rid of kids you don't like. There was a forensic case about 7 years ago where a mother was convicted of, she had 2 sons, a 2-year-old and a 4-year-old. Okay. The 4-year-old died of ethylene glycol poisoning. Okay. The mother was convicted and sent to prison for giving the child antifreeze. A year after she was in prison, her second child died of the exact same thing. There's a genetic disease which causes the body to produce ethylene glycol. Both the boys had it. If they would have listened to the mom who said she wasn't guilty, did a medical check on the child, they would have saved the second child's life. Okay? But the body develops ethylene glycol crystals in their blood, and it is toxic, and it is treatable. Okay? I forget the exact name of the disease, but it's a real interesting case because you watch the kid die and the mother's in jail. You're going, there's no way she could have done that one. So they finally did genetic testing and found out they both had the same genetic disorder. So it's not always, don't jump to conclusions, but ethylene glycol is toxic and it does taste sweet. So if you leave it out for coyotes or small pests, they're going to drink it, but so will little kids.
how is that treatable though?
Genetic counseling to what the material that the body's breaking down to produce ethylene glycol is taken out of the diet. Okay, so the body doesn't break it down. What did I do here? How did I go back so far? Okay, a lot of genetic diseases are treated by eliminating the substance that the enzyme or the defective enzyme can't reproduce or does produce in this case. Okay, so there is genetic counseling, there's treatment for it. Okay, but like I said, ethylene diol has a sweet taste. I'll look up the name of the case. I forget what it was and the name of the disease too. I'll look it up. I forget her name. A little note there. Go ahead and look that up. All right, so it's very sweet, but extremely poisonous. Okay, added to water, it lowers the freezing point and raises the boiling point. So if you put it in your radiator, it doesn't freeze at 0 degrees centigrade, it goes lower, and it doesn't boil at 100 degrees centigrade, it goes higher. Okay, so you're adding material to the water and it's increasing that range because you don't want your radiator to freeze because that'll destroy your car. You don't want it to boil because it get rid of all the water. Okay, to keep your car cool. So it does both things. It lowers the freezing point and raises the boiling point. It's called a colligative property. Okay, and that's what it looks like. That's antifreeze. Okay, very toxic, but very sweet tasting. 1,2,3 propane triol. Okay, that's glycerol. That's that you put in your skin, makes it real smooth. So propane triol, propane is 1, 2, 3 carbons. It is a triol. So there's an OH group here, an OH group here, and an OH group here. So CH2, CH, CH2. Okay, that's 1,2,3 propane triol. Very thick liquid, has a sweet taste also. Okay, this one is non-toxic. Okay, it's highly water soluble. Why would it be water soluble? Look at all this hydrogen bonding here. 3 OH groups to 3 carbons. Holy cow. You got hydrogen bonding everywhere. It's going to be very soluble in water, any polar compound. Okay. It's used in cosmetics. That's the moisturizer in cosmetic is glycerol. That's what gives it that, like in lipstick, lotion you put on your face. That gets it that viscous flow. Okay. It's used in pharmaceuticals. Okay. It's polar, it means it dissolves in your bloodstream. So it can carry medications to different areas of the body. And it's non-toxic. Okay, it's used in lubricants. Okay, it's got that very viscous feel. It is used in lubricants and is obtained as a product of fat hydrolysis. So when you break down fat, you get glycerol. Okay, that's what gives soap its lubricant ability. Everyone ever see Fight Club? That movie?
I don't know. We can't talk about it.
You can't talk about it. Fight Club was the best chemical made movie ever. Everything they did was chemically correct. They burned that tattoo on the guy's hand with the lye. Okay, that's exactly what happened. When they took that building out with that nitroglycerin, they got that from the fat clinic. They made soap from it and sold it to people, and they used a byproduct to make nitroglycerin. That's exactly what they do with it, from the glycerol in it. Okay, but it's a good movie, and it's very chemically accurate too. And that is 1,2,3 propane triol. So extreme amount of hydrogen bonding, very polar. Okay, lubricant, pharmaceuticals, cosmetics. Preparations of alcohols, how to make alcohols. Okay. Hydration reactions, we add water, H and OH. Okay. Addition of water to the carbon-carbon double bond of an alkene produces an alcohol, just like we did in chapter 11. Okay. But now we'll be able to name them and be able to predict them a little bit better. Okay. A type of addition reaction called hydration. That's an addition reaction because we're adding H and OH. We're adding the H and the OH of water. Okay, we're adding it to each side of the double bond. Requires a trace acid as a catalyst. What two things does it does a catalyst have to possess to become a catalyst? Does two things. Nobody remembers.
What was the
What does it do?
question?
Was that?
What was the question?
What does a catalyst do? Does two things that makes it a catalyst.
Speeds up a reaction or lowers its required
Activation energy.
activation energy, and it regenerates itself.
Perfect. Those are two things it does. Makes your reaction go faster by reducing the activation energy, and it has to be regenerated. It's never used up in the reaction. It's regenerated at the end of the reaction. Those two things make a catalyst. Perfect. Okay, so here's our double bond. And we have 4 alkyl groups attached to it. And we take water. Water is H and OH. So the water attacks this double bond here and opens it up. Okay, this becomes a single bond. The electrons go there and our H and OH attack it. So we have formed an alcohol with all single bonds from an alkene by a hydration reaction in the presence of an acid catalyst. Okay, so write an equation. Represent the preparation of cyclohexanol from cyclohexene. Okay. So a typical tested question would be, show me the equation. How would I word it? I'd word it like, give the IUPAC name of the starting material you would need to produce cyclohexanol. That's how I'd word it. So you got to do the reaction and you got to name what the reaction started with to get the correct answer. Okay. So write an equation for preparation of cyclohexanol. So cyclohexanol, you know, is cyclohexanol. Cyclohexene, 6 carbons in a circle. OL group is an alcohol. It's at the number 1 position. So that's what you're going to produce. Okay. You're going to have to add water across a double bond. So what's the starting material you're going to use? You have to have the shape, and you got to have a double bond for the water to attack. And this double bond opens up to form an OH and an H, which is that compound. So the starting material is cyclohexene, and it even gave it to you right here. So if cyclohexene water in the presence of an acid catalyst goes to cyclohexanol. That's the equation. And we've done that before. Remember Markovnikov's rules of where it goes. In this case, it makes no difference because same amount of hydrogen on both sides. Okay, so here's a better picture of it. So here's your balanced chemical equation. Cyclohexene plus water in the presence of an acid goes to cyclohexanol. And that's a hydration reaction. Does that make sense? Those are the same reactions we did with the alkenes, and it just forms an alcohol. Hydration of any alkene is going to form an alcohol. Write balanced equations for the hydration for each of the following alkenes. Remember Markovnikov's rule. Markovnikov's rule is very simply hydrogen likes hydrogen. Okay, and that only applies if it's unsymmetrical. If it's unsymmetrical, you get a major minor product. If it's symmetrical, you will get a 50-50 product. Okay. And let's go into it. So this is, someone name that real quick. I know you got to think back to the last chapter.
Propene.
Perfect. That's propene. Okay. Hydration. Hydration means you're adding water. You're hydrating it. So that plus H2O goes to. So let's take CH3. And here's our double bond. CH, there's an H. There's an H. There's an H. Let's open this double bond up. Okay, now it's a single bond. Okay, and we're going to add H and OH, or we can add OH and H. It can go to either side. In fact, I'll write it out a little bit better, and then we'll go through it again. So, whoa, slow down. Lost too much of my thing. So I could have added H and OH, or I could have had CH3. Again, CH, CH2. And the OH could have been here, and the H could have been here. Okay, there's two products that could be formed in the presence of an acid. Okay, it's an unsymmetrical double bond. So we got two products. Are they 50-50, or are they major minor, and which one's major minor? So first of all, is it 50-50 or is it major minor?
Major minor.
Major minor, because they're unsymmetrical. Okay, the top one, is the top one the major or the top one the minor?
Major top.
Minor is on top.
Minor's on top. Remember, hydrogen likes hydrogen. On the top one, this hydrogen has one hydrogen attached. Let's use a different color. Okay. On this one here, this hydrogen that we added has two hydrogens attached to that carbon. Hydrogen likes to be with more hydrogens. Okay, so this is your minor product. This is the major product. Remember, hydrogen likes to be with hydrogen. So this bottom one has two hydrogens. The top one only has one hydrogen with hydrogen. There's a lot of hydrogens there. Okay.
And
So
the
you can
top
have
one
more-
doesn't keep its double bond, right?
Right. That's that
Okay.
one just goes away. I can't really erase on this with this computer, right? The section here, but it's a single bond. You're right. That bond opens up. And that's a single bond right there too. Okay. So let's name, a typical question would be, starting with propene, what's the name of the major product for a hydration reaction? That'd be a typical question. Because then you got to do it, you got to figure out major, minor, and then you got to name it. So what's the name of the minor product in this case?
Propanol.
Someone said it.
Propanol.
Propanol. Perfect. 1-propanol, propanol. What's the name of the major product?
2-propanol.
2-propanol. OH group's on the number 2 position. So now let's get rid of this and we'll do it with a little more clearer here. If I can get rid of some of my writing here. It's still cutting. All right, that should give me some room. There we go. Went back too far. Means you're gonna have to go through this. Okay, so there's propene. This is a little bit clearer here. This is propene. The water attacks the double bond because the electron density there. There's a lot of electrons there, a lot of negative charge, and you can attack it with the water. You can get an OH and an H. Okay, so the major product puts the OH there. The minor product puts the OH here. Because here you have 3 hydrogens. Here you only have 2 hydrogens on the carbon of the double bond. And hydrogen likes hydrogen. Okay. So your major product is 2-propanol. Your minor product is 1-propanol. Let's see a little clearer there. All right. Name that compound.
Ethene.
Ethene, perfect. That's ethene. And we're going to do a hydration reaction again. So plus H2O. And we open up that double bond. Sometimes it's better to put the H's out like that. We open up that double bond and we add OH and H. Okay. And we can do the double bond. And we add OH to this side and H. Okay. Is this major minor or is this 50-50?
Would it be just a single product?
You got it. Trick question. It's not either. It's a single product. Both these are exactly the same thing. And how you can tell they're the exact same thing, name it. Name the top one. 1-ethanol. Name the bottom one. 1-ethanol. Because you count from the side, you get the OH group, the lowest number. If the IUPAC names are identical, it's the same compound. It's just rotated, it's just flipped around left to right, but perfect. That's just one compound. So your answer is ethanol. That's it. Okay. It's the same exact thing. If the IUPAC name is the same, it's the same thing. So it's not 50-50. It's not major minor. It's just one product. Okay. So ethanol plus water goes, ethene plus water goes to ethane, ethanol in the presence of an acid catalyst. And you only get one product form. So whenever you have a hydration reaction, you're going to have your choice between one product, 50-50, or major minor. Those are your choices. Very good. Perfect. Okay. Name this compound.
Hexene?
What's that?
Is it hexene?
Perfect. But put a number in front of it.
3-hexene.
Perfect. You got it. 3-hexene. The double bond is at the number 3 position. So that's 3-hexene. And we're going to open this up and we're going to form CH3, CH2, CH, CH, CH2, CH3. We're going to open up the double bond and we're going to hydration reaction. So we put an OH here and an H here. And we do the same thing, CH3, CH2, CH, CH, CH2, CH3. And we're going to put an OH here and an H here. And it's going to be in the presence of acid. And it's going to be plus H2O, hydration reaction. All right, so look at our products. Okay. What do we notice about those two products?
They're 50-50.
Not 50-50 because name them. Name the top one. Top one is 3, 6 carbons, hexanol, right? Name the bottom one. 3, hexanol. The exact same thing. So it's not 50-50 and it's not major minor. It's only one product that's formed. And the only product that's formed is 3-hexanol. Everybody see why? If you look at it, you take it, you flip it around, it's the exact same thing. But remember when you're given an IUPAC name, you're numbering it, you always give the OH group, the functional group, the lowest possible number. So on the top one, you start from left to right, and it'd be 3-hexanol. On the bottom one, you start from right to left, and it'd be 3-hexanol. And if it's the same IUPAC name, it's the same compound. There's no difference. So there's only one compound that's being formed. Okay. So here's your double bond. You've opened that up and you have formed only one compound, depending on which way you number it. And either way, it's 3-hexanol. Okay. Okay, preparation of alcohols, we have hydrogenation. Okay. Hydrogenation is adding what? Hydrogen. Okay, hydrogenation is to add hydrogen. Addition of hydrogen to a carbon-oxygen double bond of an aldehyde or ketone can produce an alcohol. So we can produce an aldehyde, we can produce an alcohol using an alkene and adding water, hydration. Or we can prepare an alcohol by using a aldehyde or a ketone, which produces an alcohol by adding hydrogen. Okay. Okay, it's a type of addition reaction. You're adding hydrogen to both parts of the bond. It's also considered a reduction reaction. Okay, requires a catalyst, platinum, palladium, or nickel. Has to be the catalyst formed. Okay, so an aldehyde or a ketone has a carbonyl group. Okay, the only difference between an aldehyde or a ketone, okay, is if this is an H, it's an aldehyde. If this is a carbon, it's a ketone. That's it. So an aldehyde always occurs at the end of the molecule because hydrogen's it's terminal, right? We do Lewis structures, hydrogen ends it. So aldehydes are always at the end, ketones are always in the middle. That's it. So if both these are R groups, alkyl groups, it's a ketone. If one of these is a hydrogen, it's an aldehyde. Okay, so now you have a carbonyl group. You have a carbon with a double bond of oxygen. So now we're going to attack this double bond. And we're going to add H across it. We're going to have hydrogens on both carbons. Okay, so what this does, opens up the double bond. So R, C, O, R. This double bond is opened up. And now the hydrogen is going to attack both parts. You're going to put an H here and an H here. Now you created an alcohol. So we made an alcohol from an aldehyde or a ketone by adding hydrogen. Okay, hydrogenation. It's an addition reaction just like hydration, just like water, except now we're adding two of the same thing. We're adding hydrogen across. So there can only be one product because you're adding hydrogen to both places. You cannot have an H minor. You can't have anything else. You're adding hydrogen to both sides of it. You're only going to get one product. So then we added that and we produce our alcohol. So remember, an aldehyde or ketone has a carbon double bonded oxygen. That's called a carbonyl group. The ketone is two R groups attached. The aldehyde is one of those is an H. That's the only difference. All right, so write an equation represent the preparation of one propanol from propanal. Propanal is an aldehyde. We haven't got that yet, but propanal is 3 carbons. The Al ending means aldehyde. ONE means ketone. So Al is aldehyde. So we got our double bonded carbon and a hydrogen. Because remember, aldehydes have to be at the end because they're bonded to hydrogen. So this is CH3, CH2, C double bonded OH. And we're adding hydrogen, hydrogenation. Okay, platinum, palladium, nickel, something like that as our catalyst. So far, so good. Okay, that's the starting point. That's our propanal. To get propanol, and then we have CH3, CH2, and our H. Okay, now, actually, hold on. CH3, CH2, C, we open up the double bond. Okay, there's our double bond opened up now. And we're going to add hydrogen to both sides of the double bond. So this becomes OH and this becomes H. Because those are the carbon and oxygen of our double bond, we're going to add H to both sides of it. And now we've made an alcohol, 1-propanol. So from an aldehyde or a ketone, we can add hydrogen as an addition reaction and create an alcohol. Just the same as you did with hydration across the double bond of an alkene. Okay. So this is propanal right here, 3 carbons, And again, it's an aldehyde because it's a carbonyl group. And on one side, there's a carbon. On one side, there's a hydrogen. If this was a carbon right here, then it would be a ketone. That's our only difference between aldehyde and ketone. We haven't done it yet, but that's what it is. Okay. So the carbonyl group double bond is attacked and it opens up as a single bond, and we add H and H. We're adding hydrogen. So there can only be one compound form because we're adding the same thing to both sides of the carbon. Okay, only when we're adding something different, like an H and an OH, can you get major, minor, or 50-50. This is always going to be one compound because you're adding the same thing to both sides of the double bond. Okay. Write an equation, reduction of butanol. Okay, provide the structures and name of the reactants and the products. So butanol is how many carbons?
4.
4 carbons. So CH3, CH2, CH2, C double bond O, H. It says butane is 4 carbons, all single bonds. Al means an aldehyde. And aldehydes have to occur at the end. They can't occur anywhere else but the end of the compound. Okay, aldehydes have a carbon bonded to one side of the carbonyl carbon and then a hydrogen. And reduction means to add hydrogen. Okay, oxidation is adding oxygen. Reduction means to add hydrogen. Okay. Goes to, let's open our bond up. Let's just go CH3, CH2, CH2, CH, and we're opening up this bond right here. Now that bond's a single bond. And to both sides of that, where the double bond was, we're going to add hydrogen. So we add a hydrogen here on this side of it and a hydrogen here on this side of it. Okay. So it says provide structures and name the reactants and the products. Well, the reactants that we named already is butanol. This is butanol. That's hydrogen. And this is what? What's the name of the product form?
Butanol.
Perfect. Butanol. Okay, so this is butane or 1-butanol. Either way is fine. Okay, so this is butanol. Here's your carbonyl group. And again, it has a carbon attached to it and a hydrogen. So it's an aldehyde. Aldehydes have an Al ending, just like alcohols have an Ol ending. Okay. Hydrogen in the catalyst, platinum, palladium, and nickel. And they open up this double bond, okay, to give you CH2OH. Hydrogen on one end, hydrogen on the other end. To butanol. Okay, representing the preparation of 2-propanol from propanone. Okay, this has an ONE ending. ONE ending means a ketone, which means there's going to be carbon on both sides of it. Okay, preparation of 2 from propanone. So propanone is 3 carbons. The double bond is between the carbons, so it has to be right here. That's not very clear. Okay, the carbonyl group has to be between them because this carbon is your carbonyl carbon, and it says it's a ketone, which means carbon has to be on both sides of it. So the only place that carbonyl carbon can be is in the center. That's why it's not 2-propanone. So CH3 carbonyl group. Everybody understand that this carbonyl carbon has to have 2 carbon, has to have a carbon on both sides, and there's only 3 carbons. So it has to be in the center. Can't be anywhere else. If it was anywhere else, it'd be an aldehyde. And the ONE ending means it's a ketone, and propane means it's 3 carbons, all with single bonds. So we're going to prepare an alcohol from it. So we're going to add hydrogen. That would give us adding hydrogen for the reduction gives us a alcohol from a ketone or an aldehyde. So now let's write our same compound, CH3. CH3, and we opened up our double bond. And we're going to add hydrogen to both sides, one to the oxygen, one to the carbon, where that double bond was. So we're going to have an OH there and a hydrogen there. Okay, and again, only one compound can be formed because you're adding the same thing to both sides, both elements of that double bond. You're adding two hydrogens. It's only going to form one thing. Doesn't matter which hydrogen goes where, they're both hydrogens. Okay, and the name that we formed is 2-propanol. So if we take a propanone by reduction, by adding hydrogen, and converted it into 2-propanol. And this is, what's it? Let's say nickel, palladium, or platinum. One of those two. Sometimes heat also. One of those three has to be a catalyst. Okay, so here's the reaction laid out a bit easier. Does everybody understand why this has to be in the center? You only have 3 carbons. You have to have a carbon on both sides of the carbonyl group because it says ONE, it says ketone. So there's no other place it could be. It has to be in the center. Okay, we open up that double bond. The double bond gets attacked by hydrogen. Hydrogen goes on both sides of it. So the hydrogen gets added was here and here. Once that double bond was opened up, and you have 2-propanol. You have your alcohol. Okay, reduction of butanone. Okay, butanone is how many carbons?
4.
4 carbons, all single bonds, and it's a it's a ketone. So let's make 4 carbons. Okay. Everybody see that if I put the carbonyl carbon, this is your carbonyl group right here, has to be in between the carbons. And if I put it in the second place or the third place, it's the exact same structure. Because remember, you name it to give the functional group, which is the ketone, in this case, the lowest possible number. So I put it there, we're gonna number it left to right. If I put it on the other side here, right at this point here, we're gonna name it right to left. So it's the same thing no matter what. Okay, that's why you don't have to put a number in front of it. So that's butanone. Reduction means adding hydrogen. And then we're going to take our compound CH3CO, open up the double bond, CH2, CH3, and we're going to add hydrogen and hydrogen. And we get our alcohol. Okay. So remember, ketones have this carbonyl group between 2 carbons. If one of those was an H, it'd be an aldehyde. Okay. And then this is what we produced. This is our alcohol. Someone named the alcohol.
Two butanol.
Perfect. Why do you got to put the 2 here? To distinguish it from being at the number 1 position. It was at the number 1 position, you can say butanol, but this is at the number 2 position. Just he said, perfect. Okay, so this has to be 2-butanol. Make sense? All right, so we've done addition reactions of water and hydrogen to make alcohols. We've used alkenes by adding water, hydration, to produce an alcohol. And we've used ketones and aldehydes by reduction reactions, adding hydrogen to make alcohols. Now we get dehydration of alcohol. Dehydration is the exact opposite of hydration. Instead of adding water, we're going to take water away. Okay. And we'll let's get a little bit of this and we'll call it quits about 5-10 minutes. So alcohols dehydrate, which means they lose OH and H. We lose water. Okay, with heat in the presence of a strong acid to produce alkenes. Okay, they produce a double bond back. You're doing the reverse reaction that we've done. You know, a reverse reaction, concentrated sulfuric acid or concentrated phosphoric acid. Okay, sulfuric acid is battery acid. That's strong stuff. If you ever Open up a battery, that battery acid is pretty strong. This is phosphoric acid. This is pretty strong too. This is what, if you ever had dental work done, when you had those white fillings, you know that blue stuff we put on the tooth at first to get it cleaned off on the inside? That's 34% phosphoric acid. That's this stuff. So that is strong enough to etch enamel. And enamel is pretty tough to etch. Okay, so both those acids are very strong, sulfuric acid and phosphoric acid. And dehydration is an elimination reaction. Remember, we had addition reactions. Now we're doing elimination. We're getting rid of something. We're getting rid of the water. Okay, a molecule loses atoms or ions from its structure. So you're losing H and OH. That's dehydration. Here, OH and H are removed. They're eliminated from adjacent carbon atoms to produce an alkene and regenerate or produce water. Okay, so we're going to go back and produce our double bonded alkene and water as our products. So it's a reverse of hydration. Remember, the hydration reaction forms an alcohol. Dehydration reaction forms an alkene. It gets rid of the water. All right, let's give an example here. So here's our alcohol. This is our H, and there's our hydrogen. Okay, we're going to get rid of this. They're going to combine to form water. So the bond that they have, the electrons from that bond is going to swing up into here and form a double bond. So you've gotten rid of the water. You've taken OH and H away now. It's an elimination reaction. We're getting rid of this. And it has to be on adjacent carbon atoms. They have to be next to each other. You can't pull one off a carbon atom and then one off a carbon atom way up here. Okay, they have to be adjacent. You pull this away, and those electrons that are left swing up in here and form a double bond, forming your alkene. And sulfuric acid, phosphoric acid, and heat is your catalyst. Get rid of some of those marks. Okay, perfect. So you can see you've taken this OH and H and you formed water. And the bonds swung up here to form your double, the electrons, I'm sorry, swung up into here to form your double bond. Okay, so let's use ethanol, add acid and heat. So you get dehydration reaction. You're getting rid of H and OH to form water. So the electrons that are left swing up in here to form your double bond. Okay. So the dehydration reaction of ethanol produces ethene. Okay, that's how questions be worded on your exam. Because that way you have to write the compound, know what you're doing, and then know what the answer is to come up with it. So ethanol, dehydration reaction, removing water, produces ethene. Okay. Let's see. Name the reactant we're starting with. What's our reactant? I'll give you a hint. Starts with a P.
Propanol.
Perfect. Propanol. Okay. And it's a dehydration reaction, so you can write it out if you want, a little bit different. CH. Let me write a little bit different. Let me do this here. CH3, CH2, CH2, OH. Okay, so we're going to get rid of the OH and the H, dehydration, and we're going to produce CH3, CH, CH2. And we're going to produce propene.